Final exam coming up next Wednesday, everyone, and we know that we have 10 written response questions as well as 25 multiple choice questions on that exam. I told you already, question number 1 will be a projectile motion question. Jacob was smart enough to ask, can we do a projectile motion question? Sure. Let's do that right now. Okay, there are 2 types of projectile motion questions, one of which will appear on your exam. Let's take a look at both of them. The first situation, the first type of problem is when we have a building like this or a cliff like this and something's being launched horizontally off the edge of the cliff. It will not be launched at an angle off of the cliff because that requires the quadratic equation, which many of you have never seen before. You won't have to use the quadratic equation for this or any other question. So if it's launched off the top of a building, it's got to come horizontally off the edge of the building. The other situation is when it's launched at an angle, but it's launched from the ground and then it goes back down to the ground. Someday, maybe you take a course in the university in physics or you take engineering, maybe you see a question like this, where it lands on the top of a building or a cliff like that. You can't see that on our exam because that also requires the quadratic equation, and some of you haven't learned that in math class yet. So it's either going to be what you see right there, where it's launched horizontally from the top of a building down to the ground, or it's this one where it's launched from the ground, lands on the ground, but launched at an angle. One of the 2. Let's throw some numbers in here, although we don't really have to conceptually go through the question, but we will because for whatever reason that seems to make people more comfortable when we actually see numbers. Let's say the height of the building here is 20 meters. Let's say the speed of this is 10 meters per second. Let's say the speed of this one is also 10 meters per second, but our angle is, say, what angle do you want to go with there? 30, did you say? 30 degrees, good choice. Doesn't matter what we're trying to find here in these questions, okay? Let's just set them up now. In both cases, we'll have an x component and a y component. Doesn't matter which question we have, whether it's the first one or the second one. We got an x and a y. The x component is always described by the same equation. Always. Doesn't matter whether it's problem number 1 or problem number 2. It has to be v is equal to delta d over delta t. Can anybody tell me why? Why does it have to be delta v over delta t? Delta d, I should say, over delta t. You have no other option. You know this is question number 1 on your exam. If you don't write down v equals d over delta t for the x component, there is zero excuse. I'm telling you, this is the first equation on the written response portion of the test that you will write down. Okay, if you don't write it down, then you better study harder. It has to be this one. Why? Why? As the projectile moves through the air, it follows a parabolic path, right? It goes over and down. The over motion, the horizontal motion, isn't changing velocity. It's a constant velocity. And there's no forces acting horizontally on it. There's a force acting down on it, which causes it to fall down or slow down as it's going up, but there's no forces acting horizontally. In other words, it travels at a constant velocity horizontally. And the only equation that we use to describe constant velocity is v equals delta d over delta t. So it's got to be this one. Now, for the y component, we got a few options here. For the y component, we're dealing with acceleration. So it could be any of those acceleration equations, any of those group B equations that we learned in September. But the one that it will most often be, the one that we're always going to try first, because it's most commonly appears, or most commonly solves the problem, d is equal to vit plus 1/2 at squared. Try that first. Every year, question number 1 is a projectile motion question. The reason it is because it covers both uniform motion, constant velocity, and accelerated motion from Unit 1. It covers a good part of Unit 1 for us, right? It's the best question that I can give you to cover the most stuff in Unit 1, kinematics. So every year, there's one of these on the exam. And every year, I tell people it's question number 1 on the exam. And every year, I tell people, these are the 2 equations you're going to write down first. And every year, there's people that don't write those 2 equations down. Because either they weren't paying attention, or because they didn't study hard enough and they forgot, whatever. Okay? There's lots of stuff you got to study. Okay? I told you what 7 of the 10 questions are. Okay? At least the concepts of those 7 questions. There are other ones. There are 3 other ones. Okay, that doesn't mean just because I told you 7 concepts doesn't mean you shouldn't study everything. You should, because there's 25 multiple choice questions. There's 3 more written response questions, right? But if you know that this is on there, you better make sure you know how to do this, right? There's no excuse for bombing this question when you know this question is going to be on the exam. Same 2 equations for problem number 1, problem number 2. Doesn't matter whether it's launched horizontally or at an angle. Now it comes time to plug numbers in. The horizontal velocity here is 10 meters per second. It's not launched at an angle. It's not part of that 10 horizontal, part of that 10 vertical. All of it is horizontal, 10 meters per second. Now, what's the horizontal velocity over here? 8.66 meters per second. Where did that come from? I don't even see 8.66 up there. Where did that come from? Yeah. Cos, sine, cos, tan. We don't like funny angles. Remember that? I don't like funny angles. So let's get rid of it. We got 30 degrees. Let's get rid of it. 10 meters per second, 30 degrees. Let's get x. Let's get y. Cosine 30 degrees is equal to x over 10, or x is equal to 8.66. And while we're at it, we might as well do the y component. Sine 30 degrees is equal to y over 10. Y is equal to 5. So that's off to the side there. We just got my x component to be 8.66. The y component, 5, that's not really relevant for us right now. We don't know what delta d is for the the x component here, nor do we know what delta t is. Although sometimes we might. Okay, some problem you get, maybe you're given how far it lands from the base of the cliff, not what the height of the cliff is. Okay, that's okay. Okay, we got to be prepared to think on our feet a little bit here. If we know that this is 30 meters this way, and we don't know what this is, then plug in 30 meters for the horizontal displacement. Just keep them straight, right? X is x, y is y. We don't know in this question what x is. We do know in this question what y is. We don't know what x is over here as well, although you could be given a question where you're given the horizontal displacement there. Just this one you're not. Don't know what d is, don't know what t is. Here's the first difference between these 2 problems. The horizontal velocity. The horizontal velocity is all of the velocity for the first one. If you're given 15 meters per second, 28 meters per second, the horizontal velocity is that 15 or that 28 meters per second every time. In the second question over here, it's a component of it, the x component of it. So up until this point, questions were exactly the same. At this point, it's a little bit different. We just take a number in the first problem. We have to find a number in the second problem. Okay, so we don't have anything yet. Let's go to y component. Delta d for the y component here would be negative 20. Why negative? Why negative 20? Yep, right? Good, because it goes down. It's below where it started, so it's negative 20. Delta d here for the y component would be what? Seth, what's delta d for the y component in this one, the second problem? Where does it land relative to where it started? Vertically. Yeah. Up on 0. If it starts right here and ends right here, it's gone horizontally a certain displacement, but vertically it ends up in the exact same place. So delta D for the y component will be 0. There's the second difference right there, the vertical displacement. It's whatever the height of the building is in the first problem, it's 0 for the second problem. VI for the y component, for the y component here in the first problem is what? Jacob? It's 0. It's 0. Because it's, look, if the 10 meters per second was all horizontally, then none of it's vertical. What's VI for the y component over here? Jacob? 5. There's the third difference. So we've got 3 differences so far. We've got the horizontal velocity, different. We've got the vertical displacement, different. And we've got the initial vertical velocity, different. Now, other numbers are going to be different as well, but the way we think about them isn't. Plus 1/2 of neg 9.81 times t squared. Plus 1/2 of neg 9.81 times t squared. Now, in both of these cases, the only thing we're going to be able to solve for is t. Okay? In some problems, maybe it's not solving for t. Maybe you're solving for some other variable. It should pop out to you at this point, though. When you plug in your numbers and you have both of these equations written down for either problem number 1 or problem number 2, you're going to see the one variable that you're able to solve for. I don't care what it is. Solve for it. If it's t, great, solve for it. If it's d, solve for it. Solve for whatever it is that you can solve for. Okay, so let's do it over here. Okay, let's simplify this by just getting rid of the 0 times t. It becomes negative 20 equals negative 4.905 times t squared, right, 1/2 of neg 9.81. Let's say neg 20 divided by neg 4.905. That gives me 4.077 equals t squared. T is equal to the square root of that, 2.019. Let's solve for t on the other one. A little bit harder. We can still simplify this a little bit too, but not quite as much. 0 is equal to 5 times t minus 4.905 times t squared. What's the big thing with this one? What's the tricky thing in rearranging this second one here? Jacob? Yeah. Divide everything by t, including the left side. 0 divided by t is 0. 5t divided by t is 5. 4.905 t squared divided by t is 4.905 t. Now it's a lot easier. Now it's simplified dramatically here. Let's take the 4.905 t over by adding now, because we're taking the whole thing over, including the t. And now, Stephanie, how are we going to get that 4.905 to the other side? That's right. 1.0194 seconds. All right. So we're basically in the same place in both problems here. We've just solved for the time. Maybe that's not the one you solve for on the test. Maybe it is. Doesn't matter. One of these equations will have one unknown. You need to solve for the one unknown that you have, whether it's in this one, whether it's in this one, whether it's time, whether it's displacement, doesn't matter. Get the one unknown that you have. Once you have that one unknown, you're probably going to end up plugging it into something else. Here, plug it into there and solve for delta D. Here, you're going to plug it into here and solve for delta D again. quick question. Why can I take the time from the y and put it into the x when I can't take the displacement from the y and put it into the x? I can't take the velocity for the y and put it into the x. Why can I do that with time? That was kinda. Yeah, time is equal to each other in both of them, but still we need a little bit more there. Time's a scalar. Okay, velocity is a vector. It's either x or it's y. Displacement's a vector. It's either x or it's y. Time is a scalar. So time is going to be the same no matter whether it's x or y. Okay? Yes, but you won't have a problem that's that hard. You won't end up with a question where it has two unknowns. That has two equations, two unknowns. Okay, mathematically, that's a little bit, it's doable, but it's pretty tricky. Actually, it wouldn't work in this one anyways because it would be two different unknowns, right? Yeah, it'd be two different unknowns. You couldn't have the same two unknowns in those two equations. So. Actually, that's not true. You could, but it would be way too hard for you. Okay, what else could I ask here? Well, we got the time. We got the displacement. I could ask you for the maximum height of the ball. What's the maximum height of the ball in the first question? Don't make this harder than it has to be. What is it? 20 meters. Well, you don't have to calculate anything there. What's the maximum height of the ball in the second question? That's a bit more work. Okay, that's not just reading a number off of your sheet there. Okay, let's do that now. Let's get the maximum height in the second question. When you're solving for max height, do this. Go to the y component. For the y component, once again, this time we're going to say vf squared is equal to vi squared plus 2ad. Now, at the maximum height, okay, in the middle of this projectile path, this parabolic path right here, at the maximum height, it's moving this way still, but it's not moving up or down. It's actually stopped vertically. Right? Still moving horizontally, because that's a constant speed, but it's stopped vertically. Since it's stopped vertically, and we're looking at the y component here right now, Vf will be 0. We're analyzing the trip up. And at the end of the trip up, the vertical velocity is 0. The initial velocity would be 5. In this case, the y component of that 10 meters per second. Acceleration is negative 9.81 times the displacement. We solve for delta D here, works out to be 1.27 meters. Wait a second. Does that make sense? In the first question, we got a displacement of, well, we were given a displacement of 20 meters. In the second question, we got a horizontal displacement of one value. When we plug our numbers in here, our vertical displacement was 0. Now it's 1.27 meters. What's the deal with that? When we analyzed the whole problem, the vertical displacement was 0. But when we analyze half the problem, this half of the problem, the vertical displacement isn't 0. It's 1.27 meters above the ground. Make sense? Listen, that's pretty much all I can ask you. What else can I ask you with projectile motion? That's pretty much it. There is 0 reason why you shouldn't get either 100% on this question or really close to 100% on this question. Maybe you make a silly mistake. That happens. I hope you don't, but it happens. I've made silly mistakes, and I'll continue to make silly mistakes probably, and so will you. I hope you don't do it on the exam. If you do, you'll still get a good mark on this question. But there's no reason why you can't get a good mark. You know what you're going to see. If you don't understand it, come get some help. If you do understand it, review it, do a couple practice questions. You know it's going to be there. Okay, no excuses. Next question we want to take a look at here, Carrie's requesting. That's also on our exam, a vertical circular motion question. Now, what could I ask you for vertical circular motion? A few different things, but we'll take a look at a couple of different things here. Let's say we got a bucket of water. It's in a vertical circle, or swinging it upside down. Let's say we want to find, let's say the bucket of water has a mass of 1.3 kilograms. Let's say the radius of the circle is 1.0 meters. We want to find, let's say the time that it takes to go around the circle once, or the period, let's say, is 1.5 seconds. No, let's not do that, actually. Let's first find the minimum speed. How fast does it have to be going at the top of the circle so that it doesn't fall out? Now, let's say if it's going twice the minimum speed, let's find the force of tension in the rope at the bottom and at the top. What else could we call the force of tension in the rope here? What other variable could we name it? Call it Ft, but we could also call it Fn, the normal force. We want to find the normal force at the top and bottom. So the first problem we're going to analyze is get the minimum speed. We can't find the tension at the top and the bottom until we have the minimum speed because it's based on a speed that's twice the minimum speed. So we got to get that minimum speed first. Minimum speed occurs at the top. There's the bucket of water. Okay, it's at the top of the circle. It's going to fall out. Water's going to fall out. It's going to fall out at the top, not at the bottom. We've got two forces acting at the top. We've got the force of gravity acting down, and we've got the normal force acting down. The normal force acts toward the center of the circle, right? Where the string is pulling. And we say F net is equal to the sum of the forces. When you came into the class today, there was something from Physics 30 up on the board. F net is equal to the sum of the forces. The difference there, the only difference, is that that was electric force and magnetic force combined to give you the net force. This is gravitational force and normal force. Same idea, right? Net force is also mv squared over r. Force of gravity is m times g, but the normal force is 0. When you're looking for minimum speed, the normal force is 0, always. Now in this case, we can cancel out an m because it appears in both terms. V squared over 1.0 meters equals 9.81. So we're going to say V, the minimum speed, is the square root of 1 times 9.81. We get 3.132. Or we round this to, how many digits should we be? 3.2. 3.1, I should say. There's the min speed. All right. If that's the min speed, then the speed we want for the second part of the question here is double that. So the speed now is going to be 6.264 meters per second. Okay. Is that okay? Question? What's the tension in the rope? What's the normal force acting at the top of the circle at that point? Hey, it was 0 a minute ago at 3.1 meters per second, but at 6.2 meters per second, not going to be 0. Rope has to pull to keep it in the circle. The normal force acts down. The force of gravity acts down. We're going to say F net is equal to the sum of the forces, Fn plus Fg, same as we did in the last question, the last part of it. mv squared over r equals Fn plus Fg. M's don't cancel here because it doesn't appear in every term. What was the mass of that thing? 1.3 kilograms? Now, we've plugged numbers in here. We got to worry about signs. Really, we should have worried about it up here too. This was negative because they were both down, but they canceled. Here, mv squared over r is negative because it's acting toward the center of the circle. Gravity is negative because it always acts down. Can't cancel them out there. Solve for Fn. Solve for the normal force. Let's take 1.3 times 6.26 squared divided by 1. Let's get that number on the left-hand side first. You get negative 51.009. Get the number on the right-hand side, then take it over by adding. So let's add to 51.009, 1.3 times 9.81. I solve for Fn, and it works out to be negative 38 newtons. Make sure you can get that number. Negative 38. It's a negative number. It means it's downward. It should be. You're at the top of the circle. The normal force has to be pulling you downwards. Okay? On which part? This part? I get the negative on that part because F net stands for the centripetal force. The centripetal force always points towards the center. If you're at the top of the circle right here, and this is the center of the circle is downward from you. So that centripetal force must be pointing downward toward the center. Now, we didn't draw it. We didn't draw it in there because it's really Fg and Fn combined. But that combined force is toward the center of the circle. It has to be. If they're both acting down, and they both give us the centripetal force has to be acting down as well. No, don't do that. No, don't put a negative in until you plug a number in. Okay. Listen, if you're going to put a negative in, you might as well just follow the procedure, right? Instead of putting a negative in for the normal force, because we know it's going to end up being negative, let's put a negative in for the numbers that we know. Right? We know this 1.3, 6.26, the 1.0. We know those numbers. We know the sign of it, so let's just put it in. Okay, let's not make it harder than it has to be. Louis? Yeah. So having a little bit of trouble finding that number. Let's go through that then. Let's say, what do we got here? Let's get the left-hand side. Let's say 1.3 times 6.264 squared, squared, divided by 1 equals 51.009. But that's a negative number, so let's make that negative. There's my left-hand side. Make sense? Okay, negative 51 right there. Now, this number, 1.3 times 9.81, whatever it is going to get taken to the other side by adding, because it's taken away from Fn. So let's add to that 51.009, 1.3 times 9.81. See why we're adding that? It's downward. It's a negative value, so it's like subtracting it. Take it over to the other side by adding it. That leaves me with only Fn on the right-hand side. Gives me negative 38 newtons. That make sense? Yep. Yep. Finally, we want to find the tension in it at the bottom. Normal force acts up. Gravity acts down. F net is equal to Fn plus Fg. mv squared over r is equal to Fn plus mg. Mass is 1.3. Speed, 6.264. R, 1. Now, Carrie, you were asking about the centripetal force last time, why we should make it negative. Well, this time it's going to be positive. How do you know it's positive? Fn and Fg are opposing each other. How do you know that Fn wins? Well, if it stays in the circle, if it's going around the circle, the centripetal force has to point toward the center, and the center is up. So Fn is, the centripetal force has to be a positive value there. Gravity is still going to be negative. Now, Lewis, how are we going to solve this one? Let's say 1.3 again times 6.264 squared divided by 1. This time it's a positive number, not a negative number. Let's still take the 1.3 times 9.81 over by adding. Which gives us 64 newtons. That works. That works for me for two reasons. One, it should be a positive value. That's what we got. Two, it should be bigger than the normal force at the top of the circle. The normal force at the bottom will always be bigger than the normal force at the top. Always. Because gravity and the normal force are opposing each other. Normal force has to be stronger to beat gravity. Okay, at the top of the circle, gravity and the normal force are working together. Kind of like a tug of war. Top of the circle is when everybody's on the same team pulling in the same direction. The bottom of the circle is when you're pulling in one direction, somebody else is pulling the opposite direction. When do you have to work harder? When you're pulling in opposite directions, right? That's going to be a bigger force. Third request we got here for going over a problem is yet another question that will appear on your final exam. Conservation of energy. What kind of problems can we see with conservation of energy? Well, lots, but the most common one is something that looks like this. It's a roller coaster. Let's say the height of this is 40 meters. Let's say the height of this is 20 meters. 10 meters. And 30 meters. Let's say the roller coaster car at the beginning of this is moving at 4.0 meters per second. The question now is, how fast is it moving here? And, well, we could do it in a million different places, right? Let's do it over here. How fast is it moving here? How fast is it moving when it's down to 20 meters? How fast is it moving when it's gone back up to 30 meters? Well, let's do the green one first. When we get a problem like this, we know we're going to do this EI equals EF thing. The energy stays the same. It gets converted from one form to another. Right? We start off with a little bit of kinetic and a lot of potential. It gets converted to more kinetic and less potential as it goes down. But the total amount of energy still remains the same. So let's say EI is equal to EF for this green problem here. The energy that we have at the beginning of this problem is two types. We got potential energy because there's a height, mgh. We have kinetic energy because it's moving, mgh plus 1/2 mv squared. Now, if there was an elastic or a spring that was stretched or compressed, there would be elastic potential energy, but there isn't. When we get over here, what kind of energy do we have? You got to ask yourself the same questions, right? Do we have a height? Do we have a speed? Do we have a spring or an elastic? Carrie, what do we got there? Yes, because there's a height and it's still moving at that point, right? Now, in this case, masses cancel only because it appears in every term. If it doesn't appear in every term, don't cancel it. It's good news for this question because we weren't even given the mass. So let's sub our numbers in here now. Then I put it 1 times 40 plus 1/2 of 4 squared. The final height is 20. All right, so let's get what we have on the left-hand side here first, okay? Let's say 9.81 times 40. Okay, that's the first term. Sorry, say it again. Doing the green one here right now. Doing the first one. 9.81 times 40 is 392.4. Let's add to that, use some brackets here, 0.5 times 4 squared. Okay, there's the left-hand side. Now, 9.81 times 20, we got to take over to the other side, the left side, by subtracting, because it's added to the 1/2 v squared. So let's subtract from that 400 on the left side, 9.81 times 20. When we do that, we get 204. Now, we got to get rid of the half. We can multiply by 2 to get rid of that half. Or the alternative to that is divide by half. Multiply by 2 or divide by half, doesn't really matter. Then let's square root that. We end up 20.2 meters per second, or V would be 20 meters per second. Now, let's do the blue one, height of 30 meters. What's your prediction? It's moving at 20 meters per second. Coincidence or not? The height of 20, started at 4 at a height of 40, moving at 20 at a height of 20. Is our new speed going to be 30 meters per second? What do you think? How do you know for sure that it won't be 30 meters per second? Before you do a single calculation, how do you know that the speed won't be 30 meters per second? In other words, how do you know that that was a coincidence that we got 20 meters per second there? Zach? Good. It ends at a higher height. It's going to be moving slower than 20, not faster than 20, right? So it's not going to be moving at 30 meters per second. Let's figure that out now. EI is equal to EF. Now, you can make your EI either here or here. It doesn't matter. Let's go back to the beginning again. EI is what we started off in the first problem. MGHI plus 1/2 MVI squared equals, over here, we've got potential and kinetic energy as well. M's cancel because it appears in every term. 9.81 times 40 plus 1/2 of 4 squared. We're going right back to the beginning of the problem. Now, if this, let's call this A, B, and C. If A equals B and A equals C, then B would also be equal to C, right? It doesn't really matter, because we only need to set either A equal to C or B equal to C, but bottom line is the energy at all of these points is equal to each other. That's conservation of energy. The final height is 30 meters. We're going to solve this the same way. Okay, so we're going to say 9.81 times 40. Okay, that's the initial potential. Let's add to that, brackets 0.5 times 4 squared. That's the left-hand side. Now, let's take 9.81 times 30 over by subtracting, because it's added to 1/2 v squared. Let's multiply it by 2 or divide by 1/2. Now, this is equal to VF squared. Let's square root that. And we end up with 14.5 or 15 meters per second, which we didn't have a number. We didn't predict an exact number, but we knew it was going to be less than the original, right? We knew it was going to be less than the 20 meters per second that we got in the first question. Carrie? Yep. I'm sorry? Oh, no, I understand your question now, yeah. Good. Carrie's question was, guys, listen up here. Carrie's question was, since we know that EI equals EF, we don't have to stress about the 10 meters in between, right? Correct. It's irrelevant. It doesn't matter. Listen, it could have went up like this. Well, not that high, because it wouldn't have went that high, but It doesn't matter where it goes to, right? Maybe it goes straight across like this. Doesn't matter what's in between. What matters is initial and final. It's EI equals EF, not EI equals E in between F-ish. Right here? Well, I mean, conceivably, you could be asked to solve for the speed there as well, but it's not relevant to solving for the speed there. It's only relevant if you're asked to solve for the speed there at that point, right?